Okay, now it's recording. So anyway, be sure you do everything on the presentations, both chapters. Be sure you do everything on the worksheets for both chapters. There may be a few questions from the sampling assignments from both chapters, and then there will be a few questions from the previous two chapters, 1 and 2. So pretty much the same thing as what we did for exam 2. And I believe that is it. Does anybody have a question now? Okay. Oh, yeah, Gary. Chapter 7. Okay. Okay, hang on just a second. Well, I mean, you could start reading it, but you're going to be studying for an exam. I would hold off till maybe next week on that, you know, because you got an exam you're going to be studying for. So I think I would wait a little bit longer on that. But thanks for asking. I got a question here I haven't responded to. For the exam, do we have to memorize the solubility table? Yes, ma'am. The one that we had in the actual PowerPoint presentation. So not the one that you see in Blackboard. Oh, wait a minute, no, there isn't one there. No, the one that's in the presentation. It's a little bit smaller than a lot of them. Looks like I got another question here. Oh no, I already did that one. Okay, I think I have answered everybody's chat questions. So unless there's another question, yeah, Jessica, you have a question?
Yeah, going back to like the test, is there a specific time we have to take it at, or is it any time on Monday?
Oh, maybe you had a question.
What?
Okay, if you think of something later, go ahead and you can ask. So we're gonna get back into our current chapter, and so I need to put that up here. But not that. Let's try this. So it's been a little while because we had that Friday off. So anyway, according to what I have, we stopped off at slide number 11. So we'll jump through these real quick. So we were talking about wave properties, and then we're talking about electromagnetic spectrum, photoelectric effect, continuous versus line spectrum, energy levels, which translates into orbitals, and the Bohr model of the atom. And then we started on quantum numbers. And the first quantum number being the principal quantum number, it's going to be an integer greater than 0, so no negative integers. Then we went to and we talked about how that has to do with the probability of a location and energy. And then we got into angular momentum quantum number, which has to do with the shape of the orbital. And it can be any number starting at 0 and going to whatever the principal, or n, is -1. So if n is 1, then you can only have 0. Or if n is 2, then you could have 0 and 1. We did that previously. And then we talked about how these convert to 3 or 4 letters: S, P, D, and F, 0, 1, 2, and 3. Then we went to the magnetic quantum number, which has to do with the direction that an orbital is facing. But we only went to just the case of where the angular momentum is 1, because then you could have -1, 0, and +1, and that would be like X, Y, and Z coordinates on a Cartesian coordinate. We then went to this table. We'll make this bigger. There we go. Maybe that's easier to see. Anyway, oh, did it one time too many. There we are. And so this first column here is the different values that n can be. Notice it's not 0, it's not negative. It goes 1, 2, 3, 4. Possible values for L, or the angular momentum quantum number, what those can be. Then we convert it in from the number into the letter to get this kind of designation. Then we saw the different values for the magnetic quantum number. And then we're talking about how many different orbitals you could have based on these. So you see 1, 2, 3 gives you 3 possible. And if we're looking at its whole level together, we've got the 3 here, the one above it, that gives us 4. And then the next slide was spin quantum number. You can only have 2 values, -1/2 and +1/2. And then that was where we stopped off. And then we got going on a worksheet. But before I put this away, has anybody got a question on these first, let's see, what is it? First 11 slides? Okay, not seeing anything there. Then I'm going to put this away and we'll get back into the worksheet that we were on. So we were on the quantum number worksheet. You guys were in groups, and we went through everything on the first page, and then we went to the second page, and we did this first question. So what I'd like for you to do is to go into Blackboard. Let me throw that up here real quick. Okay, looking at Blackboard, you go to Course Materials, and then you go down to the worksheets, click on that. Then you go to the one for electronic structure, click on that folder, and then click on the one for quantum numbers. When you do that, you're going to see the same thing we were just looking at over in the other view. So now I'm going to go back and stop that, because you guys will need to be able to look at that to do this second page. Now, we did the first question on that one. That is so we did this question right here, part A, where the principal quantum number n is equal to 2, the angular momentum is 1, the magnetic is 0, and the spin is a +1/2. And what we said was that these are valid numbers, because what the question you're answering is, for any of these sets, are they not valid? And if they're not valid, why are they not? But if they are valid, what would be the designation for that orbital? So for this first one here, A, we said that it was 2p. I don't remember who answered that, but somebody did. So what I want to do now is put you guys in your group so you can talk to each other about the answers, and I want you to do, B through E of question 7, and then A through C of question 8, and A through F of question 9. But what I'm going to do is I'll give you some time to get started on these first ones, and then I'll start calling on groups for someone in the group to give us the answer for it. So has anybody got a question before we get started? Okay, I'm gonna go ahead and activate the groups. No, I'm going to have to change a few things before I can do that. Sorry, folks. This should only take a second. Had a few people that came in a little bit later, so I need to put you in your group. Okay, I'm going to start the groups. If you see you're in the wrong group, send me a chat message and I'll move you to the correct group. So here we go. Space, and it's got some way of designating it, you know, like 24C or something like that. And then that's the only parking space, or a better one would be a seat in a theater. You know, you got a row and you got a letter, and that's the only, you know, that's the only seat that has that particular combination of number and letter. Except here we got four things instead of two things. So that's a way to think about it. Is it's very much like either parking spaces, seats in a theater, something like that. So anyhow, does anybody have a question? Because we're going to go back then into the chapter 6 PowerPoint. And we're basically doing two things in this PowerPoint. We are either doing quantum numbers, or we're then going to take orbitals and figure out what's the orbital for a different atom. So anyway, what we got here in this picture is these are orbitals using the number and the letter designation. So like down here where it says 1s, that's principal quantum number 1, and then that's going to be angular momentum 0, because s is equal to 0. And then the next one we have up here is principal quantum number n equals 2, and then angular momentum is again 0, or s. And then the next level we got up here is it's going to be 2, and now the angular momentum is going to be 1, so you've got negative 1/2, 0, positive 1/2. So that's what this is about. And what we're going to see is that there's only certain possible orbitals, and you may have encountered some different ways of doing those that were incredibly painful. Hopefully, what we're going to do won't be. But anyway, on this slide, one more thing I want to point out, and that is this thing of whoops, don't have a marker going. This thing of degenerate orbitals. Degenerate orbitals means that you can have multiple orbitals, but they're at the same energy. So I know that you may think, okay, sorry, May, that your message went by so fast, I got to go back and pick it up again. Okay, I get a lot of things. Oh, yeah. Well, don't do that. I don't know. Anyway, yeah. Okay, degenerate orbitals. The idea there is it's orbitals that are on the same principal quantum number. So the n is the same, or the other way of saying it is the energy is the same for that entire set of orbitals here. I'll make this bigger so you can read it. But anyway, N is the same, or the energy is the same. So for the 2p, we've got 3 orbitals that are on the same, have the same value of N. They're at the same energy level. Since there's 3 orbitals, you can put a maximum of 2 electrons per orbital. So the maximum we could have in here in the 2p then is going to be 6 electrons, 2 electrons per orbital. And then we've got the 3p that's just like the 2p. We've got the 4p, it's just like the 3p and the 2p. And then up here at the top, we've got the 3d. So now at this point, D then is going to be equal to 2. So then the possible values of M are going to be, -2, -1, 0, +1, +2. Or the other way to think about that is altogether, that is 5 different orbitals, just like we have up here. 1, 2, 3, 4, and 5. Those are all they all have the same principal quantum number. It's going to be 3. They're all on the same energy level, so we call them degenerate orbitals. And this doesn't mean a whole lot to us right now. It'll mean more later on. Okay? So now looking at the next slide. This is sort of the same thing, and just showing how the orbitals fill. You can put 1 electron in the 1s, you can put 2 electrons in the 2s, but when you get to a third electron, like when atomic number is equal to 3, then now that third electron is going to have to go into the 2s. Then if you have 4 electrons, you can put electron to the 2s, but as soon as you got 5 electrons, you have to put that 5th electron in one of these 2p orbitals. We'll come back to this a little bit later on, but I just want to get you to start thinking about that. Okay, now let's look at this. Express how many electrons are in which orbital, and that is what electron configuration does. It's the number of the electrons, and then it's indicating, they're saying subshell, they're indicating which orbital those electrons are in. So in this case, we have 1 electron in the 1s orbital. So N equals 1, and then angular momentum equals 0 or equals S. And remember, the angular momentum is giving you a shape. Sorry, my writing is going pretty fast here. So if it's a s orbital, the shape is like a ball. The only other one that we're going to consider is a p orbital, and that's going to be shaped like a dumbbell. We'll get to that a little bit later. So now let's go to our next slide, unless somebody has a question. You can always raise your hand if you got a question, to stop me. Okay, let's go to the next one. Now, you maybe ran into this horrible thing before, the filling order diagram. And personally, I hate these things. But anyway, the way you do this, you have to draw this thing out. So you start and you draw. I'm going to change colors here. The red. You do 1s, then below that you do 2s, and below that you do 3s, and so on. And then when you get to the 2s, well, after you do all your s's, then you can do your p's. And there is no 1s, or 1p. There's only a 2p. So then you start in there, 2p, 3p, 4p, so on. Then you can go to your Ds, but you cannot have a 1 or a 2D. You can only have a 3D. So you start at 3D and 4D. And then when you get to the Fs, you cannot have a 1, a 2, or a 3F. You can only have a 4F. So you start in there. So anyway, you draw this whole thing in, and then you start drawing diagonal lines. So like you see this one going through here, and then it's sort of going back, and then it's going through 2S. So this means you fill 1S, you fill 2S, then the line goes back, then you fill 2P, 3S, then it goes back again, you fill 3P and 4S, then you go back, then you fill 3D, 4P, and 5S. Now you can see there's a lot of ways you can mess this thing up, so I don't really like it. So I was going to show it because you guys have probably seen it before, but I don't think it really works very well. But if you've really had it beaten to your head in like a high school chemistry class or in Chem 110, then, go for it. But otherwise, I'm going to propose a different way to do this, and we'll see how that goes here. Just a second, please. Okay, why is that doing that? No, 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 no. No, okay. Anyway, and that is to use the periodic table. You're always going to have a periodic table in front of you. Okay? So since you're always going to have a periodic table, you might as well make use of that. So there's a couple things you will need to do, though, to use the periodic table. Take helium and put it over here for this purpose. Now, the rest of the time, we're going to keep it over on the right, and we're going to say it's a noble gas. But for what we're doing right now, put it over there right above beryllium. Then that will give you a block on the left, and that block is going to be the S block. That's the one where the angular momentum number is going to be 1. Then we can go to the right side, and we can take what is left after we took helium away, and we can draw a square around that, and that's going to be the P block. M is going to be, I just did that wrong. Nobody said anything. M is not equal to 1. M is equal to 0. Over here on the P block, M is equal to 1. Then we've got this block in the middle. I'll draw a rectangle around it. This down here is the D block. So M equal 2. And then this weird strip that we always have just sort of left over, that's going to be the F block, and or M equals 3. Okay, is everybody good with that part? S, P, D, and F. Because I'm going to erase it and then do something else. Okay, not seeing any hands or anything, so I'm going to erase. Can't see it. Oh, Gary, man, you're probably on that iPad again. Anyway, well, I'll talk through it. You take helium, move it over to the left side of the periodic table, and put it above beryllium. Then take those first 2 columns, one that starts with hydrogen, and then the one next to it that's now going to start with helium, and call that your S block. Oh, really? I don't know why you're not seeing it. Weird. Well, we've got another picture that will help you. Also, you can look at this one, and you see how if you really make it bigger, you can see that there's S's on all the ones on the left. Then over on the right side, starting at boron, going over to neon and everything below it, that's going to be the p orbital, or the p block. And then in the middle part where the transition elements are, so you got scandium going over to zinc and everything below those, that's the D. And then all those radioactive elements like cerium and those in that area, those are going to be the A block. then what we can do is we just go in the order of atomic number. So hydrogen is over here on the left. It's got one, its atomic number is 1. It's got 1 electron, and that's going to be then in a 1s orbital. Then right next to that is going to be helium, and it's got atomic number 2, so it's got 2 electrons, and those are going to be in the 1s orbital. Then we come down to the next row, and we're looking at lithium. We're back over on the S block again. Now you got atomic number 3. You have 3 electrons. 2 of those are going to be in the 1s, and 1 of those electrons is going to be in the 2s. And then we just keep doing that kind of thing. We get to beryllium, and it's got 4 electrons. It has 2 electrons in the 1s, 2 electrons in the 2s. But then when we get to boron, when we get over to boron, then it now has a 5th electron. That 5th electron is in the p block. So it is in the 2p. See, everything across there is on the 2nd level. Whether you're over on the left side where the s orbitals are, or if you're on the right side where the p orbitals are, those are all on the same row of the periodic table. So boron is going to have 1 electron in a 2p orbital. The rest of them are going to be in s orbitals. And you keep going across there. Carbon, you got 1 more electron, so on. You get the neon, then you're going to go back over to the left. You're going to be at sodium, and it's going to have all the previous electrons that we already described, plus it's also going to have 1 more electron, and that's going to be in a s orbital. It's on the 3rd level, so it's in a 3s orbital. And then if you look at magnesium, it's got 1 more electron, and that 2nd electron is also going to be in the 3s orbital. But when you go over to aluminum, just over to the right, it's got 1 more electron that's now in a p orbital, but it's on that same level, the 3rd level. So far, everything seems pretty easy to do. And then when you go down to the 4th row on the periodic table, it's going to work the same as the 1st and the 2nd and the 3rd rows, where they're all going to start out with a 4, and it's either going to be a 4s or a 4p. But you got that transition elements there in the middle, and that's where things get a little bit, you got to think a little bit differently. As soon as you go from calcium over to scandium, as soon as you cross over to the transition, the D block, you have to decrease the principal quantum number by 1. So if calcium is 4s, then when you go to scandium, it's going to be 3d, not 4d, 3d. And then everything just keeps working like that until you get down to cesium, down there in those green, in that green box. Down there, it has an F orbital. Whenever you transition into F from the S block, so when you go from S block to the F block, the principal quantum number decreases by 2. So if we were at, say, barium, on the 6th row of the periodic table, look at the 6th row periodic table, you'll see cesium, and then next to that you see barium, Ba. That's on the 6th level. When you move over then to cerium, whenever you move over into the F block, you have to decrease the principal quantum number by 2. So instead of being 6, it's going to be 4. Anybody got a question on what I was doing? Because to me, it's a lot easier to just use a periodic table and remember that when you transition from the S to the D, you decrease the number by 1, and when you transition from the S to the F, you decrease it by 2. That's all you have to remember, and you have a periodic table. I think that's a lot easier than using this thing and having to draw it out. But again, if you've been doing it this way for a long time, you can go ahead and stick with what you know. Okay, I'm not seeing any questions, so I'm going to keep moving. So now, oops, Gary. Can't I write it on? You can, but you're not going to be able to use your periodic table when you do an exam. It is something that you need to remember. So you'll always have a periodic table. The periodic table will always look like the ones that I've given you before, but you'll have to use the ones with the exam. Okay, so what we're going to do now is we're going to go through the through some of the elements, not all of them, because that would be really annoying. And we're going to, for each element, we're going to do two things. We're going to see what their electron configuration is. This is hydrogen. And then we're also going to do a orbital diagram. And orbital diagrams, you represent an orbital either with a box like you see on this slide, or it's going to just be with maybe a horizontal line. Oh, that's painful writing that out. Sorry, guys. Oh. So over there where it says 1s1, that's an electron configuration. Right next to it where there's a box 1s underneath, that's an orbital diagram. So hydrogen is atomic number 1. It only has one electron that we have to account for. So that one electron, which is the superscript right after the S in the electron configuration, it is in the 1s orbital. Or if we're doing an orbital diagram, we just draw a single box, put underneath the box 1s, and show there's one electron in there. Now let's go to helium. So for helium, now it's atomic number 2. There's 2 electrons we have to account for. Those 2 electrons are going to be in the 1s orbital. So the orbital diagram, the orbital diagram is going to be the box with the 2 arrows in there with 1s underneath. Or the electron configuration is going to be 1s2. Now let's keep going in atomic numbers. So next we would have lithium. Its atomic number 3 has 3 electrons. 2 of those electrons are in the 1s orbital. So it looks just like it did for helium as far as the 1s orbital goes. There's 2 electrons in the box. But there's a third electron, because there's 3 together. That third electron goes in the next row of the periodic table, and it's going to be in the 2s orbital. And then when we get to beryllium, it's got 4 electrons. 2 of those are in the 1s, and 2 of those are in the 2s. Now at this point, now we're going to be putting electrons into the p orbital, and we've got to pay attention to a few things if we're doing a orbital diagram. So if it's boron, you now have atomic number 5, 5 electrons. 2 of those are in the 1s, 2 of those are in the 2s, and 1 of them is in the 2p. If you're drawing a orbital diagram like you have on the right-hand side of the slide, it really doesn't matter which box you put the electron in. They're all the same. They're all degenerate. They all have the same energy. So you could put it in any of them. It wouldn't matter. Now, here's where we have to watch, though. As soon as we go to one more electron, like you have in carbon, when I went from boron to carbon, now we've got 1, 2, 3, 4, 5, 6 electrons, atomic number 6. That 6th electron, you cannot put it in a box that already is occupied. So you single electrons in degenerate orbitals first. Again, when you got one more electron in the 2p, you can't put it in the same box. The reason why is that electrons have a negative charge. That charge is going to be repelled. They're going to want to avoid each other. And so the best way to do that is to put one electron in one of these orbitals and one in the other. I just noticed I got some stuff in the chat here. Let's see if there's anything I need to say anything about. Oh, okay, no, there isn't. Okay, let's put in one more electron. No, let's put in two more electrons. We're going to skip nitrogen for right now. We're going to go right to oxygen. So now I've got 1, 2, 3, 4, 5, 6, 7, 8 electrons. 2 electrons in the 1s, 2 electrons in the 2s, and then 4 electrons in the 2p. As soon as I got to that fourth electron, then I have no choice but put it in a box with another electron, put it in an orbital with another electron. But notice that in the picture, one arrow is pointed up and one arrow is pointed down. Now that would be the same as saying one of those is 1/2 spin number and the other one is -1/2. Now we don't know which one is +1/2 and which one's -1/2, and it has to do with not having a reference frame, and it's not a problem anyway. Just remember that one's going to be up, one's going to be down, one's going to be +1/2, one's going to be -1/2, but anything beyond that, we don't need to know. Just make sure that in all the previous cases, don't pair the electrons until you have no choice but pair the electrons. So we can go now to this slide, and this is showing you everything from nitrogen to neon. So up here with nitrogen, it doesn't have carbon. We did that before, but when we get to nitrogen now, you've got one electron in each of those 2p orbitals, those 2p boxes. We move to oxygen, we now have to pair them. We have to go to fluorine, we got to pair one more, and when we get to neon, we got to pair one more. And this thing here with neon, and it being a noble gas, and being what we are going to say is essentially non-reactive. The reason why it's non-reactive is it does not have any unpaired electrons. You have to have unpaired electrons for something to be reactive. Now, I just noticed it's 1:50. We need to leave. Anybody got a question before you take off? Okay, I don't see anybody on that. So remember, we're going to have a lab on Wednesday. Come to the collect room first, and then I'll send you off to do the lab. Otherwise, you guys have a good day. Try to be safe. Be careful, and I hope to see you on Wednesday. So you guys take care.